This is AP Review FRQ number 2, curve sketching. This is with calculator. The function g is defined with g of 1 equals 2, but what's provided for us is the first derivative function, which is sine of x plus 1 over x, and also the second derivative function, 1 minus 1 over x squared times cosine of x plus 1 over x. Find all the values at which the graph of g has a horizontal tangent line. So we don't have the graph of g, but we do have g prime. So if we want to find the horizontal tangent of g of x, then that's basically where the slope of g of x is 0. And if we're trying to locate where on the original g of x graph has a slope of 0, we can pinpoint the x-intercepts on g prime, because g prime tells us about the slope of the original function. So wherever g prime has an x-intercept will be where horizontal tangents occur for g of x. So we look for x-intercepts. So we can graph this function. We can set between 0.1, 2, and 1. And when we do that, we may have to adjust the y-axis a little bit just so that we can zoom in on the points that we're concerned about. So we're concerned about this point and this point. And to find this point here, we can do second trace, choose 0, and this is between 0.1 and 0.2, and I get 0.163. Now, you see negative 2e to negative 13. That's basically a really, really small number. Basically, we can think of that as 0. It's basically a 0 there. And then if we go through that process again, second trace 0, we can find the other critical point being 0.359. Okay, part B, on what subinterval is the graph concave down? So what we can do is we can use the calculator to give us fg double prime, and if we want to find out where our graph is concave down, we can use the second derivative function. So this is a picture of the second derivative function to find our critical points, and then also to test the intervals, and from there decide where our interval is concave down. So if we plug this in our calculator, we get a graph something like this. Our endpoints are 0.1, 2, and 1. Those are our boundaries. Our critical points, where f double prime is equal to 0, where potential points of inflections are, is 0.129 and 0.223. And then we can just look at the graph, right? If we're dealing with the second derivative function, the location will tell us whether the original graph is concave up or concave down. So anywhere that g double prime exhibits a value above the x-axis, that means that's a location where the original graph is going to exhibit concave up. Below the x-axis is concave down. Above the x-axis is concave up. So we can create a sine line out of this, and we know that our original graph will be concave down in this middle interval from 0.129 to 0.223, since g double prime is less than 0. Part C, write the equation for the tangent line. So equation of tangent line requires order pair and slope. So to find the slope, we have the g of x, g prime function, so we can just plug 3 into g prime and make the calculator do the work for us. We get negative 0.472. But if we want to find the point, we have to rely on this original function and displacement. So anytime I'm looking for a position and I'm only given an initial position and displacement, I got to combine those two together. So if I want to find my y value at 0.3, I need to start at g of 1, and then I have to find the displacement from 1 to 0.3, basically going backwards, but we're going to make the calculator do the work for us. We get 2 minus 0.077, which is 1.546. So the order pair is 0.3, 1.546. Our slope is negative 0.4722, and then we do point slope form. Okay, part D, does the line tangent to the graph of g at 0.3 lie above or below the graph of g? So we want to know, does this tangent line going to sit above the original g of x graph or below the original g of x graph. And this is how we can tell. We look at the behavior of the second derivative function. Now, the second derivative function between 0.3 and 1, between 0.3 and 1, it's clearly in the concave up behavior. So if a graph is concave up, this is what our original graph could look like. It exhibits a concavity, positive concavity in this interval. Then any tangent line that is going to skim the surface of this graph at a given point will always have to be below the actual curve. It's going to be an under approximation of the actual curve. So the tangent line to the graph will always sit below the curve if the curve is concave up. Now, likewise, if a graph is concave down, then any tangent line that is on the graph that is part of a concave down behavior will always over approximate, will always sit above the actual graph. So that's an important concept for us to understand, that we can tell whether a tangent line sits above or over approximates, and the other option being sits below and under approximates, just by looking at behavior of concavity. If it's concave up, then the line is going to under approximate. If it's concave down, if the graph is concave down, then we know our tangent line is going to over approximate.